In September 1913, a wealthy German engineer named Rudolf Diesel boarded the mail steamer SS Dresden in Antwerp, bound for Harwich, England. He dined that evening with two business associates, retired to his cabin around 10 p.m. and asked to be woken at 6:15 the next morning. He was never seen alive again. His cabin bed hadn't been slept in. His watch was found neatly placed on the nightstand, stopped. 10 days later, a Dutch pilot boat spotted a decomposed body floating in the North Sea and pulled from its pockets a pillbox, a wallet, and a pocket knife his own son would later identify. That sounds like the ending of a thriller. But the story of the diesel engine, the machine now powering roughly 90% of the world's cargo ships, starts decades before that night, with a young man obsessed with a single radical idea that machines were wasting almost all of their energy, and that this waste was, in his words, a moral failure. So how did one engineer's crusade against inefficiency end with him vanishing into the sea, on the eve of a war his invention would help decide? Rudolf Diesel was born in Paris in 1858, the third child of German immigrants Theodor and Elise Diesel. His father ran a small leather goods workshop, binding books and crafting fine leather cases for a modest but steady clientele. It was not a wealthy household, but it was a stable one, until 1870, when the Franco-Prussian War broke out and shattered that stability overnight. France, gripped by anti-German panic, began expelling German nationals from Paris. The Diesel family was given almost no warning. Rudolf, just 12 years old, was separated from his parents and put on a train alone, carrying a small bag and a letter of introduction to a family friend in London. He arrived in a city he had never seen, speaking almost no English, uncertain if he would ever see his parents again. That kind of disruption shapes a person. Diesel spent the rest of his life chasing control, mathematical, mechanical, near absolute control over forces that seemed too large and too chaotic to master. Some historians have speculated that this early trauma, the experience of watching a stable world dissolve into instability without warning, planted the obsession with order and efficiency that would define his entire career. Within a year, Diesel was reunited with his family in Augsburg, in the German state of Bavaria. There, a relative recognized the boy's unusual aptitude for mathematics and mechanics and helped enroll him in a technical school. Diesel excelled immediately, and in 1875 he was accepted into the Royal Bavarian Polytechnic of Munich, one of the most prestigious engineering schools in Europe. He graduated in 1880 with the highest academic marks the school had recorded to that point in its history. One lecture at the Polytechnic changed the direction of his entire life. His professor, Carl von Linde, himself a brilliant engineer who would go on to invent modern refrigeration, taught his students the principles of the Carnot cycle, a purely theoretical model first proposed by French physicist Sadi Carnot in 1824. The Carnot cycle described mathematically the absolute maximum efficiency any heat engine could ever achieve. Here is the number that would haunt Rudolf Diesel for the next 15 years of his life. The steam engines running Europe's factories, mills, and railways in the early 1880s converted only about 10% of their fuel's stored energy into usable mechanical work, 10%. The other 90% simply vanished, radiated away as waste heat, lost in friction, lost in inefficient combustion. To most engineers of the era, this was simply an accepted cost of doing business. Steam power had transformed the world already. A bit of wasted heat seemed a small price for the Industrial Revolution. To Diesel, it was something closer to an outrage. He believed, with an almost religious conviction, that a dramatically more efficient engine could do more than save fuel. He believed it could redistribute economic power itself. In his writings, Diesel argued that centralized steam plants, massive, expensive, requiring enormous capital investment, had trapped small workshops, independent craftsmen, and rural industries in a position of permanent dependence on large industrial conglomerates who owned the power infrastructure. A smaller, dramatically more efficient engine, he reasoned, could be owned and operated by individuals. It could decentralize industrial power, the way, decades later, the personal computer would decentralize computing power. Diesel wasn't just chasing a mechanical breakthrough. He wanted to rewire who held economic control in industrial Europe. For over a decade, he worked this problem quietly on paper, testing thermodynamic models, refining equations, discarding failed concepts. In 1893, he finally published his theoretical foundation, a 76-page technical paper titled Theory and Construction of a Rational Heat Motor. In it, Diesel proposed something radical, an engine that would not need a spark plug or any external ignition source at all. Instead, it would compress air to such extreme pressure that the air itself would become hot enough to ignite injected fuel on contact. On paper, the mathematics were elegant, almost beautiful. In a workshop, that elegant theory was about to nearly kill him. Diesel needed capital and manufacturing expertise far beyond what he could provide alone, so he approached two of the most powerful industrial names in Germany. Friedrich Krupp, the arms and steel magnate whose factories would later arm the German military through 2 world wars, and Maschinenfabrik Augsburg, a manufacturing firm that would eventually merge into what we know today as MAN. Remarkably, both agreed to fund him. Diesel was given a private workshop, a small team of engineers, and enough capital to begin building a working prototype based on his theoretical paper. The first prototype ran in February 1893. It exploded, the cast iron cylinder. Unable to withstand the extraordinary pressures Diesel's theory demanded, pressures far beyond what any commercial engine had ever attempted, blew apart violently during the test run. Diesel was standing close enough to be seriously injured by the blast and spent several weeks recovering. The theoretical engine that was supposed to prove pure thermodynamic elegance had very nearly turned its own inventor into a footnote. Most investors, faced with an exploded prototype and a hospitalized engineer, would have pulled funding on the spot. Krupp and Mann, remarkably, did not yet. Diesel rebuilt the design, reinforced the cylinder walls, adjusted the compression ratios downward to something the materials of the era could actually survive, and tried again. The second prototype, tested in 1894, ran, briefly, for about a minute. The engine actually worked, producing power under its own compression-ignition principle before a mechanical failure shut it down. It was the first proof that Diesel's radical theory wasn't just mathematics. It was real. 3 more years of grinding, expensive refinement followed. Failed seals, cracked components, repeated redesigns of the fuel injection mechanism, which needed to introduce fuel at exactly the right pressure and timing into an environment of extreme heat and compression. Diesel's backers grew increasingly impatient. The project had already consumed vastly more time and money than anyone had originally projected. Then, in 1897, Diesel produced a version of the engine that ran continuously, reliably, and achieved something no engine in recorded history had ever achieved: a measured thermal efficiency of 26%, 26%, against the steam engine's 10%. Stated plainly, that number doesn't sound dramatic. It was. This decision seemed small at the time. It was not. A handful of German industrialists deciding to keep funding a man whose own invention had already tried to kill him. That single decision, made quietly in a boardroom in the early 1890s, would eventually reroute the entire 20th century's supply of food, fuel, and firepower. By 1898, Rudolf Diesel was one of the wealthiest and most celebrated engineers in Europe. He licensed his patent aggressively across the continent and overseas, collecting royalty payments from manufacturers in Britain, France, Russia, Austria, and the United States. In America, the brewing magnate Adolphus Busch personally purchased the manufacturing rights for $250. Zirzen, an almost unthinkable sum at the time, equivalent to several $1 million today. Diesel's engine wasn't just an engineering triumph anymore. It was becoming a global industrial standard, and Diesel himself was becoming a very rich man. At the 1900 Paris World's Fair, the same exposition that introduced the world to the Eiffel Tower's observation decks and the first moving walkway, Diesel unveiled a version of his engine running on an unlikely and almost poetic fuel, pure peanut oil. It worked smoothly and efficiently. Diesel believed his engine's flexibility, its ability to run on multiple types of fuel including plant-based oils, could one day liberate struggling farmers and colonial economies from total dependence on imported coal and refined petroleum controlled by distant industrial powers. It was, again, never just an engine to him. It was a tool of economic liberation, a mechanical argument for a more distributed, more independent industrial future. But behind the public triumphs, the royalties, the World's Fair demonstration, the growing global reputation, Diesel's personal finances were quietly unraveling. He had made a series of poor speculative investments outside his core engineering work. He had also over-licensed his patents to manufacturers who lacked the technical skill to build the engine correctly, producing faulty, underperforming machines that damaged Diesel's reputation and triggered years of expensive legal disputes over patent rights and quality control. By some accounts, by 1913, despite 2 decades of licensing income from one of the most important machines of the industrial age, Rudolf Diesel was close to personal bankruptcy. It's a detail his own family reportedly did not fully understand until after he disappeared, and at the exact same moment, his personal finances were collapsing. His invention was attracting a very different and far more dangerous kind of attention, not from farmers, from navies. If you are finding this interesting, hit subscribe. We cover stories like this every week, and you will not want to miss what is coming next. Here is the part most people never learn about. By 1912, Diesel's engine possessed a property no other power source on Earth could match. It combined extraordinary fuel efficiency with the ability to run without the massive volume of intake air that a gasoline engine requires, meaning it could operate effectively in an enclosed, oxygen-limited space, like the inside of a submarine hull. Germany's Imperial Navy had already begun installing diesel engines in its U-boats by 1912, and Britain's Royal Navy, recognizing the threat of falling behind, was racing to catch up, negotiating for access to diesel manufacturing capability of its own. Diesel-powered submarines could travel farther on a single fuel load, remain submerged longer, and strike with far less warning than any vessel that came before them. Within just a few years, that capability would help make submarine warfare one of the deadliest and most controversial military tactics of the First World War. A war that hadn't officially begun yet, in September of 1913, but one that every industrialist, diplomat, and naval officer in Europe could feel approaching. And this is exactly where Rudolf Diesel's story takes its strangest and darkest turn. On the night of September 29, 1913, Diesel boarded the SS Dresden in Antwerp, en route to a business meeting in London tied to a new diesel engine manufacturing facility being built in partnership with the Consolidated Diesel Engine Manufacturing Company, a firm with direct ties to supplying Britain's Royal Navy. He dined that evening with 2 associates from the Dresden's crew, discussed business matters that appeared entirely ordinary, and retired to his cabin around 10 p.m., instructing the steward to wake him the next morning at 6:15. He was never seen alive again. When crew members entered his cabin the next day, his bed had not been slept in. His nightclothes were laid out, untouched. His watch sat neatly on the nightstand, stopped at a specific time. His hat and neatly folded overcoat were found on the ship's deck railing, near the stern. 10 days later, sailors aboard the Dutch ship Coetzen, patrolling the North Sea near the mouth of the Scheldt estuary, spotted a body floating in the water. Given the severe state of decomposition and the maritime customs of the era, the crew did not bring the remains aboard for full identification. Instead, they retrieved personal items from the body and returned the remains to the sea, a common practice for merchant vessels at the time. Among the retrieved items, a pillbox, a coin purse, a folding knife, and a spectacle case. Days later, in Antwerp, Diesel's own son, Eugen, examined the items and formally identified them as belonging to his father. No formal cause of death was ever confirmed. No autopsy was possible. To this day, over a century later, no conclusive answer exists. 3 theories have circulated ever since, each pointing toward a different kind of tragedy. The first theory, suicide, driven by mounting personal debt and professional humiliation. Diesel's wife, Martha, later revealed that before his departure, he had given her a small handbag with explicit instructions not to open it until the following week. Inside, investigators found a substantial sum of cash, along with financial documents outlining the severity of his debts. Evidence, some historians argue, that Diesel anticipated he might not return from the trip. The second theory, assassination orchestrated by agents connected to Germany's military and industrial establishment, intended to prevent Britain from gaining unrestricted access to advanced diesel-powered submarine technology on the eve of a war that German military planners increasingly saw as inevitable. The third theory, elimination by rival petroleum and coal interests, threatened by an engine explicitly designed to run on alternative, non-petroleum fuels, an engine that, if it succeeded at scale, could someday undercut the growing global grip of the oil industry. No physical evidence has ever definitively confirmed any of the 3. What we do know is grimly concrete, and it happened fast. Within 10 months of Diesel's disappearance, the war his technology helped make possible had begun. German U-boats, every one of them powered by an engine descended directly from Rudolf Diesel's original design, went on to sink more than 5,000 Allied merchant and naval ships during the First World War, killing an estimated 15,000 sailors and civilians in the process, including over 1,000 aboard a single vessel, the RMS Lusitania, in 1915. The engine, designed by a man who dreamed of liberating small workshops from centralized industrial power, had become one of the most effective and feared weapons of mass destruction of the early 20th century. It liberated farmers, it armed submarines, it outlived the man who built it, under circumstances nobody has ever fully explained. The diesel engine did not remain confined to submarines and battleships for long. Its raw efficiency made it irresistible to industries far beyond the military, and the interwar decades saw it spread with remarkable speed across nearly every sector of the global economy. By the 1920s, diesel engines had begun replacing steam power in locomotives across Europe and North America. A diesel locomotive needed no fireman shoveling coal into a furnace, no massive onboard water tanks, and none of the hours-long startup process required to build steam pressure before a train could even begin moving. Railroads that made the switch from steam to diesel cut their fuel costs by roughly a third and dramatically slashed maintenance downtime. Since diesel engines required far less constant mechanical attention than steam boilers, by the 1930s, diesel had moved decisively into commercial trucking agriculture, and heavy construction machinery. Its characteristic high torque at low engine speeds, ideal for hauling enormous loads from a dead stop, made it the natural choice for the trucks, tractors, bulldozers, and cranes that would go on to physically build the highways, farms, dams, and cities of the mid-20th century. The very infrastructure of modern industrial civilization was, quite literally, constructed using engines built on diesel's compression-ignition principle. Then came global shipping, and this is where diesel achieved something close to total dominance. After the Second World War, as international trade expanded at a pace never before seen in human history, diesel became the unquestioned standard for cargo vessels of every size. It wasn't a close competition. Diesel engines could run continuously for weeks at sea on relatively inexpensive heavy fuel oil, hauling tens of thousands of tons of cargo across oceans at a fraction of the operating cost of any realistic alternative. No other technology came close to matching that combination of range, reliability, and cost efficiency. By the latter half of the 20th century, diesel had also conquered European roads in a way gasoline never fully managed to. Fuel taxation policy across countries including Germany, France, Belgium, and the Netherlands favored diesel fuel for decades, encouraging automakers to build increasingly refined and powerful diesel passenger vehicles. By the early 2000s, diesel-powered cars accounted for more than half of all new vehicle sales across much of Western Europe, a level of market dominance diesel never achieved in North America or much of Asia. The machine that exploded violently in a small Munich workshop in February 1893 had, within a single human lifetime, quietly become the invisible infrastructure holding up the modern industrial world. Consider the scale of what that infrastructure looks like today. An estimated 90% of everything transported across the world's oceans. Food, electronics, raw materials, medicine, fuel itself, currently moves on cargo ships powered by diesel engines that trace their lineage directly back to Rudolf Diesel's 1897 design. Roughly 300 million diesel engines are estimated to be in active operation globally at this moment, spanning cargo ships, freight trains, long-haul trucks, farm tractors, backup generators, and construction equipment on every inhabited continent. Nearly every hospital's backup power system, the one that keeps ventilators and surgical equipment running during a blackout, routes through a diesel generator. Nearly every piece of heavy equipment that built the roads, bridges, tunnels, and skyscrapers around you relied, at some stage of its own supply chain, on diesel-powered machinery. The global diesel engine market today is valued in the hundreds of billions of dollars annually, a figure that dwarfs the entire annual education budget of most nations on Earth combined. It built fortunes. It armed navies. It moved the food that fed the population growth of the entire 20th century, and it continues moving the food that feeds the world today. There's something quietly unsettling about how enormous power can move through history without ever announcing itself. Diesel didn't build a smartphone or a spacecraft, something that visually screams its own importance. He built a metal cylinder that compresses air and burns fuel inside it. It doesn't glow. It doesn't compute. It doesn't sit on a desk demanding attention. It just runs, hidden below the decks of container ships and under the hoods of freight trucks, doing the invisible labor that quietly makes almost everything else in modern life possible. That is the recurring pattern with the technologies that actually reshape history. The Internet didn't look revolutionary in 1969 when it was 4 university computers exchanging small test messages. The assembly line didn't look revolutionary inside a modest workshop in early 1900s Michigan, and a compression ignition engine that once violently exploded in a Munich laboratory certainly didn't look like the machine that would go on to help sink 5 Susan ships and move 90% of the entire world's cargo trade. Power, it turns out, rarely announces itself when it first appears. It accumulates quietly in the background, year after year, decade after decade, until one day you look around and realize it's holding up literally everything around you, and you never even noticed it happening. Look around the room you're in right now, somewhere in the supply chain of nearly everything within reach of you. Your clothes, your food. The device you're watching this video on, a diesel engine did some portion of the invisible work required to get it there. A container ship crossed an ocean burning it. A freight truck delivered it, burning it. A generator, somewhere in a warehouse you'll never see, kept the lights running on it. Rudolf Diesel set out to free small workshops and independent craftsmen from dependence on centralized industrial power. Instead, almost by accident, he built one of the most centralizing forces in modern economic history, an engine so essential, so deeply embedded in global trade and military power, that entire economies now depend on it functioning without interruption every single day, without most people ever thinking about it at all. He never lived to see any of it unfold. He vanished into the cold water of the North Sea on a September night in 1913, just 10 months before the war that would prove, with horrifying clarity, exactly how powerful and how dangerous his invention truly was. If this story surprised you, hit subscribe and leave a comment telling us which part surprised you the most.